So maybe a quick round of introduction will be good. So I'd like to know from which place you are in, which program, which year of either BSc, MSc or PhD, whatever. Because I understand one or two probably are from beginning of their PhD career. Yeah, I don't know how many PhD students are here. So your fellowship has got enhanced, and the postdocs also. I'm trying to implement it from today. Let's see whether you get it. It depends on how long I take it here to go back in office and implement that. Okay, so let's start from the first row. Yeah. Maybe, you can pass on the microphone. Yeah.
Good morning, everyone. I am Jawahar Raja from Indian Institute of Astrophysics and Solar System Division under VSRP program, and from Indian Institute of Remote Sensing under Dr. Prakash Chaukan sir, doing solar astronomy in solar filament related researches, long-term researches, observation based doing in my native is Coimbatore. I am very thankful for this opportunity.
So you finished your master's. When did you finish your master's?
I completed my master's this year.
When was it? This year.
Yes, sir.
Okay. But now your VSP program in IA is over, or it's going on?
Last month is it over, sir.
Okay.
But project is ongoing, sir.
Project you can go on
Yeah.
forever. So that's not a problem. Okay, you can pass it on.
Hello everyone, I'm Pranjali Sharma. I'm from IIT Indore. I recently completed my MSc in astronomy there. I did a project on predicting sunspot time series using machine learning algorithm under the supervision of Dr. Amit Shukla.
Dr. Amit Shukla?
Yes.
Okay, Samit is working on sunspots?
No,
That's
actually,
big news.
no, his area is actually in AGM.
High
but
energy, yeah.
But he recently got a little bit interested in machine learning, and I was interested in machine learning.
Yeah, there are other people working. What's Saurav or what's
Yeah,
his name?
Saurabh does.
Saurav, he wants
Yes,
also
yes.
machine learning.
Yes.
And there is a girl who is doing her PhD. She's collaborating with us, Himapriya.
Yeah, right.
So she visits us,
Okay.
at least once or twice she has already visited. So that's also on some machine learning.
Mhm.
Yeah, I will talk about those very start of those projects today also. Yeah. So you finished your MSc from IIT this year?
Yes, in June. Yes.
Okay.
Hi everyone, myself Sribala. I'm coming from Kerala in the district of Kollam, and I recently completed my master's from the University of Kerala. I have been a part of project or based on exoplanets as well as globular systems of galaxies, and solar physics is completely a new area for me, and I hope to get more expectations from the same. And thanks again for the opportunity.
Good morning, everybody. Myself Karan Sahu, and I am pursuing PhD second year in NIT Rourkela. My research area is solar wind and space weather prediction under supervision of Dr. Sushant Kumar Visway.
So Sushant has been our also former student from IA. Yeah, I mean, I'm saying from our because I still have a faculty at IA. So yeah, okay.
So hello everyone, my name is Aryan and currently I'm doing my BTech in engineering physics from IIT Roorkee, and I am trying to cope up with the lectures.
Very nice, very nice. So as you know, we have a now joint PhD program with IIT Roorkee. In fact, the interviews will happen in few days' time. Your faculties will be here for the interview board. So which year of your so this is BTech Engineering Physics 4 year or 5 year?
4 year.
4 year. It's not BSMS like the Bombay IIT.
No. Currently I'm in second year.
Okay, you have just started.
Yeah,
Now, I think you have used the right word. You're trying to cope with. The thing is, where do you pitch your lectures is always a challenge in terms of your, your educational background, your subject area thing, because some of them have already got solar physics. So that's been a challenge for us also to select students. So sometimes the selection is slightly, becomes very tough to make this balance. So we have received complaints that why we have not been selected and all that. We had 200 plus applications this time. So I hope you can cope with it. But please feel free wherever you are not able to understand. Don't feel shy, because we understand that your background doesn't allow you to understand everything.
Hello everyone, myself Abhay Singh Rawat. I am from HNB Garhwal University. I am currently doing my masters. My second year has just started and I am loving the lectures.
Good morning, everybody. My name is Janvi Agarwal. I'm from Pune, currently interning with Ayuka. I got introduced to solar physics by 3 people, Dr. Helen Mason from NASA, Sherry Chabra from NASA, and Dr. Durgesh Tripathi from Ayuka.
Helen is actually not from NASA. She's from University of Cambridge.
Yeah.
But the program was supported by NASA. So.
Yeah, right.
Yeah.
So she is very helpful, and all those, whichever I have doubts and everything. So yeah, I'm trying to learn more about it now.
So when you mentioned that you have got exposure, means you have started doing some work with them?
No, not work exactly. Actually, she visits Pune very oftenly.
Yes.
So she meets, actually my guide from Masters, Raka Dabade, is
Right.
our friend.
Okay.
So like that, I got introduced to her. So I met her a couple of times, and now she's like helping me with if I'm stuck
So
somewhere.
you did your masters from Ferguson?
Ferguson College, yes. Under Raka Dabade ma'am only.
So you finished your masters?
Yes. In physics only in this year.
This
May.
year.
Yeah.
Okay. So, I mean, I was just curious. So quite a few of you will be busy with your interviews and all that also.
Yeah.
So these interviews are all going to be next few weeks.
Yeah.
So you're going to appear for some of those interviews?
Which interviews exactly?
PhD interview. I mean, if you're interested to carry on.
I would love to like give an interview, but I have not like
Got any
appeared
calls?
for any entrance yet.
Okay. So you're taking some.
Yeah.
Okay.
Yes.
Hello everyone, myself Kartik Goke. I'm from Varda, Maharashtra, and I completed my master's last year from Nagpur University. I recently completed an internship under Tanmay Samanta sir, which is based on the solar physics at Kodaikanal Solar Observatory. And thank you for this opportunity.
So how long this project was with
3 months
you were in Bangalore or you were in Kodaikanal?
in Kodaikanal, sir.
Tanmay has been my former student also. So.
Hello. Hello, sir. My name is Vaishali Bhavle. I completed my master's from Ferguson College, Pune in 2022. And I recently completed my project internship from Kodaikanal Solar Observatory under the guidance of Vagesh Mishra. And my project work was on the study of dynamics of CMS in inner corona. Yeah, thank you.
Hello, everyone. I'm Krista. I'm currently doing my 3rd year BTech in Computer Science from School of Engineering, JNU. So I have a dual degree program there. So I can even do my master's in computer science over there. So I was interested into astrophysics. So I applied for the workshop and I got in. And I'm trying to grab my head over the concepts here. So I think it will be a learning opportunity for me. I've previously done an ML project in disease prediction. So I had mentioned it. Maybe because of that I got in. So there are a lot of machine learning projects going on. Thank you for the opportunity. Thank you, everyone.
Yeah, good point. I mean, in astronomy in general, we are also involved with big data science. And data science demands not only image processing, also handling large volume of data. And automation is the key. And with AI/ML jumping in, problem is AI/ML is too much now. You have to be a little more selective. If you let ChatGPT, control the future, then it's a problem. So judiciously, we have to use it. So that's why the background is also very important. That what is the data, what kind of solution you're looking for. So that way, yeah. So it's important to have motivated engineering students who are interested in doing physics oriented problems. And that's why I had couple of very bright MTech PhD students, and both of them are now having in a very good position in US. So there are enormous scope for engineering students to come into astronomy. but you have to be motivated. And for that, just not the data alone, you need to understand or need to enjoy the physics of it. Otherwise, data handling is just, it's a tool, but you have to be motivated for the physics problem. So that's it. So today, actually, it's fantastic. Astronomy made history yesterday. I guess most of you are aware. It's amazing that in a single day, two such major discoveries, path-breaking discoveries can change the thing. Solar physics is tough to compete with such sophisticated. We can imagine the kind of data what people are talking about, and how much time it takes to reach that goal. See, this was already known for last 20 years, but the data was not, good enough to make that announcement. So it took 20 years for people to all across the globe to work on a problem, and how collective, wisdom gives you that discovery is actually fantastic, demonstration. And India is part of one of the major things. The neutrino part is not so much we have participated probably. It's unfortunate that our neutrino program was also not approved. Otherwise, probably we would have had a larger community also by now. Although the neutrino observatory program was initiated more than a decade back, but it was not supported. But GMRT has made a huge difference. So that's why the radio community, pulsar community was growing. I mean, again, I don't know how many of you are aware that the pulsar thing started from, again, Bangalore. Raman Research Institute studied this, physics of pulsars 3 decades back. My other namesake, Dipankar Bhattacharya, who is in Ashoka now, they've in early 90s, they were working on, pulsar physics. So unless you do not understand the pulsar radiation and its timing, now it's everything based on timing. And this timing work was done in early 90s by Dipankar and its supervisor Srini, and so on. Yeah, it's a fantastic day actually that way. Yeah, please go on.
Good morning, you all. Myself, Ritika. I am in my first year of master's program from JNU. I am interested in solar physics and radio astronomy.
Okay, good.
Hello everyone, I am Suraj Kumar Tripathi. I am basically from Odisha, but I study at Indian Institute of Space Science and Technology, Thiruvananthapuram. I am in the dual degree program, currently in the final year. So that was a BTech in engineering physics and master's in astronomy and astrophysics. And I have my final year project under Krishna sir and Dipankar sir. Yeah, thank you.
Hello everyone, my name is Himani and I am a PhD student at NIT Delhi. And recently I had completed my VSP program at IIA Bangalore under Vemma Reddy sir.
Hello everyone, I am Panchajanya De from ISC Bangalore. I just completed my second year BS program. Currently, I am doing a project under Professor Vaibhav Pant on prominence oscillations. I'm glad for this opportunity.
Good morning, everybody. I'm Aninda Gudia from IISc Bangalore. I'm also in second year Bachelor of Science. I'm finished my second year, and I'm doing a project on star formation with Saurabh sir over here. And I have some experience in high energy astrophysics.
Hello everyone, I'm Devesh. I'm doing my master's in physics from IIT Bombay, and I'm here working under Dipankar sir himself on automatic detection of coronal holes using machine learning techniques. Yeah.
Hello everyone, I'm doing my master's. I just completed my first year in master's from IIT Dhanbad, and I'm doing a summer project here under Santosh Joshi.
Hello everyone, myself Adarsh, and I am working on actually I'm working on galaxies, and I'm from myself Bhopal, and like I am in my final year, so I am currently doing my final year master's thesis project, and I am here for a project with Dr. Suvendu Rakshit. I guess I was really, I wanted to learn more about solar physics and Dipankar. So yeah, I was.
Good morning, sir. Hello, everyone. My name is Sakti Singh, and I am from Pataudi, Haryana. And right now, I'm doing PhD under the supervision of Dr. V.S. Pandey from NIT Delhi. And I'm enjoying the lecture. Thank you, sir. And I would like to mention one thing, that when I come to that field, I hear a name, Dipankar Banerjee, Dipuda. So it's like a dream for me to meet sir and take his lectures and some suggestions for my PhD. Thank you, sir. Thank you so much, sir.
I hope I can live up to your standard and expectation.
Good morning, everyone. My name is Deepa Varthwal. I'm a second year master's student at Kumaon University. Currently, I am enjoying the lectures. Thank you.
You're in second year of your master's.
Hello everyone, my name is Nutan Patni and last year I completed my master from DSB campus Nainital. My specialization was high energy physics and this subject is new for me but I'm enjoying it. Thank you.
Hello, my name is Anjali and I'm from IIT Roorkee. I've completed my 1 year master's program and I'm new to solar physics and I'm loving it.
But IIT Roorkee also has been part of the time pulsar timing. Armugam was involved, I think. Yeah, Armugam and one of his student or postdoc, yeah, was involved. Yeah.
Good morning, everyone. I'm Ritika Sharma. I'm currently pursuing MTech in Photonics from IIT Roorkee. I'm currently working under Professor Sumanta Sarkar on the effects of space weather events on Martian atmosphere.
Hello, sir. My name is Richa. I will be starting with second year of my MSc Physics program at IIT Roorkee in a month. And I'm having a good time learning here.
Hello everyone, myself Diksha Joshi. I am pursuing MSc from DSB campus Nainital. Thank you for this opportunity.
Good morning, everyone. My name is Kavita Krayat. I'm from DSB campus Nainital. Now I'm doing MSc in physics. Thank you.
So I'm just curious. So your Nainital, most of the students, you also did your BSc here or from somewhere else? Somewhere else. So you stay in the hostel here? PG. Okay.
Hello everyone, I am Arjun Kannan. I'm from Mysore, Thiruvananthapuram. I just finished my 4th year BSMS. I did a 1-semester project with Dr. Nitin Yadav on the detection of vortex structures on using simulated data. So I'll be continuing that for my master's thesis. So this was one of the main motivation for me to join this workshop. Thank you.
Good morning, everyone. My name is Mayank Kumar from Pandit Ravi Shankar Shukla University, Raipur. I am MSc final student. My specialization is astronomy and astrophysics.
Hello everyone, my name is Sanjay and I'm from Haryana. I'm doing PhD in UPS Dehradun and I'm working in solar physics under Krishna sir. Thank you.
Yeah, so good morning everyone. Myself Rahul and I have completed my master's from JNU Delhi recently. And my thesis, my dissertation is on the topic fluid instabilities in solar wind. And yeah, attending the lectures has been an honor for me, standing in front of these diversified people coming from various parts of the country. And it's a lot more learning here in this workshop. So thank you very much for the opportunity.
With whom you were doing the project?
Sir, under Ram Prasad Prajapati, sir. Yes.
It was more theoretical, analytical work.
Hello everyone, I am Amrit Datta. I completed my master's from IIT Guwahati and I worked on the project under Dr. Santavrata Das and also here with Dr. Saurav Sharma. So solar physics is quite new to me and I am looking at it as a first exposure to this subject.
Hello everyone, I am Niranjan. I am right now in my final year of my BSMS from ISA Mohali and I'll be doing my MS thesis project under Dr. Indranil Chaturvedi from here. After this workshop, I'll be starting my project. And both of us were here last time with IAS SRF as IAS SRF fellows. So yeah, solar physics has been a new field to me and I'm enjoying the lectures. Thank you so much for the opportunity.
Hello everyone, my name is Kanchan Jangle. I just completed my BSMS 3rd year at ISA Berhampur and currently I'm working on slow-sine oscillation under Dipankar sir and Krishna sir.
Hello everyone. My name is Yamini Pandey and I come from Pithoragarh. Currently, I'm pursuing masters from DSB campus Nainital. Here we have astrophysics as a specialization, but that does not involve too much of solar physics. So I'm just trying to learn here. Thank you.
Hello everyone, my name is Disha. I pursuing my MSc in physics from DSB campus Nainital. Thank you for this.
Good morning, sir. Hello, everyone. My name is Satyam Nirbal, and I have just completed first year master from IIT Roorkee. Thank you.
Good morning, everyone. I'm Asma, and I'm studying at ISA Tirupati. I've just completed my BSMS third year, and here I'm doing an internship with Dr. Neelam Panwaran, Star Formation. Thank you.
Good morning, everyone. I'm Mariam. I'm from Kerala. I just completed my second year BSc from Marathnesius College. I'm here doing an intern project under Dr. Vaibhavan under studying of CMEs.
Hello everyone, I'm Karthik SB. I'm from ISER Tirunananthapuram. I just finished my first year MSc, and here I'm a project student under Krishna sir. I'm working in solar acoustic halo effects. Thank you.
Good morning, sir. Hello, everyone. My name is Sunil Yadav, and I am currently in fourth year of my BSMS from ISER Berhampur. And yeah, I'm interested in solar physics. That's why I'm trying to get more knowledge about solar physics as much as possible. Thank you for this opportunity.
Good morning, sir. Hello, everyone. Myself, Sachit Upadhyay. I am from Mumbai. I just completed my first year of masters from University of Mumbai, and I will be doing project under Dr. Anil Raghav on CME anisotropy. Thank you.
CME anisotropy. Okay. With whom? Anil.
Anil Raghav.
Is in Bombay IIT?
Yes. No. I'm not IIT Bombay. University of Mumbai.
University of Mumbai. So, okay. But you go to either the CBS or somewhere? I mean, are you? Okay.
Good morning, sir. I'm Naga Shreyas from Christ University, Bangalore. I just completed my master's last month, and my MSc thesis was on the topic prominences under the guidance of Dr. Sajal Kumar Dara.
Oh, Sajal Kumar Saha.
Dara.
Oh, Sajal, but Sajal is not in the country.
Yeah, he's in
So you
Netherlands.
only did that.
It was online.
Good morning, sir. Hello, everyone. My name is Akanksha Dubey, and I'm doing MTech from CS from IIIT Hyderabad. And actually, I want to do the project, something related to astrophysics and computer science. That's why I have applied for this workshop. And I will be applying for PhD next year for the astrophysics, the field of. Thank you, sir.
Good morning, everyone. I'm Meenakshi Mandal, and I have my specialization in condensed matter physics from Parul University, Vadodara, Gujarat. I got introduced to astronomy through ETSUA this year, and I was here. So it's really a nice opportunity to be back here. Thank you so much.
Good morning, sir. I am Sambit. I have completed my fourth year BSMS from ISER Berhampur, and I am going to do my master thesis under Dr. Gajendra Pandey from IIM Bangalore.
So your master thesis allows you to be in sort of, whatever institute for how long?
For 6 months.
6 months.
Good morning, sir. Myself, Anurag Kashyap. I'm from IIT BHU. Actually, I just completed my first year and doing my project under Dr. Abhishek Kumar Srivastava, sir.
Hello, everyone. I'm Akshay Sudhakaran. So I recently completed my master's project on the dynamics of small-scale transient under Dr. Vaibhavan. So I would like to continue PhD in solar physics after this as well.
Okay, I think, yeah, the rest of our around 2 our PhD students here and there, probably you will be meeting them. Yeah, I've taken a little time off with the talk. So let's see how much I proceed with this title, because this is too big a title to cover. So I will give you a glimpse of some ground-based observation and then talk about the long-term study of the sun, where some of us are heavily involved with the data from primarily from Kodaikanal, and then we are using data from wherever. So this plot I will come back later on. This is the sun, its behavior for last 100 years. Okay. So, okay. So in terms of ground-based observation, so first statement which I would like to make is modern day astronomy demands coordinated observations from ground and space. You cannot just do in one wavelength and just do study the astrophysical objects, whatever your object is, because majority of the astrophysical objects emit in many different frequencies or wavelengths, and they represent plasma corresponding to different temperature and energies. So unless you have a full wavelength coverage, you will not see the entire object. You will see only part of the object, whether either it is its surface or its atmosphere, depending on what is the temperature distribution of this. So as you can imagine now, any modern day astronomy demands, multiple wavelength. And of course, we had great optical, satellites or X-ray satellites. But then again, new infrared domains are, opening up completely new avenue. And sun has actually shown the example many decades back. So we have been launching multi-wavelength satellites in early 90s, and that has really made a remarkable change. But having said that, we started going to the space only, in 70s onwards, I would say. So the sun has been observed for last 400 years from the ground, and some of the data has been recorded by hand, by drawings and so on. Some of the records have started, being in the form of photographic plates and images and so on, which has been now digitized to make it compatible with the digital format, which we are using for last, say, 4 decades or so. So the last, the CCDs came in early 90s. So that way, the digitization demands to connect with the older history. So that is what also something I will talk about. Interestingly, Kodaikanal is one of the oldest observatories in the globe, completed 120 odd years now. We have Udaipur Solar Observatory in the beautiful Fatehsagar Lake. We have a facility with a modest half-a-meter telescope, but it is also a station for GONG. GONG is a Global Oscillation Network Group. It is part of an international National Science Foundation project where identical telescopes are placed across the globe at 6 stations so that we can continuously look at the sun. Because like we are observing the sun, well, not now today, but we can observe from India, but the Europeans are still sleeping. Americans are hard in the, dark now. So to continuously watch what is happening in the sun, you need to have ground-based facilities all across the globe, or you go to the space. So a combination of ground and space now providing us a continuous coverage. So GONG was such a project. And again, GONG was initiated way back in 80s, and from mid 90s, we have that facility at Udaipur as well. And of course, you haven't had a visit to the this telescope, which is just a few hundred meters from here. Probably one of these morning, if the sun is, okay. But they can go up, na? Yeah, we can find that out. Yeah. But again, in this condition, the telescope cannot be opened. If it suddenly becomes bright and sunny only, it can be opened, because the moisture is also a huge problem. So this is a 15 centimeter H-alpha telescope, which is there at that location. So that's the, optical facilities. But we have radio facilities, which is, as you know, GMRT probably you only know as a, extragalactic, eye, but GMRT can be also used for solar observation. Since it is a high demand for extragalactic sources, we don't get time for solar observation. But, this is too, sun is too bright for GMRT. So we can't use all the, 37 telescopes. Interferometry is not required. Only single dish can do the job. So occasionally, solar observations are actually taken from GMRT. We have a radio antenna array in Gauribidanur where there is a heliograph. And so it can do polarimetry and other observations also. So if people are interested in radio domain, with just imaging and polarimetry and so on. One can use Gauri-Bidanur. Also, there is a IPS, interplanetary scintillation, observation possibilities from UTI. UTI is again TIFR's facility. In fact, GMRT was born out of UTI's experience. Professor Govind Swarup, who is the father of Indian radio astronomy, he started all his work from UTI. He was actually situated in UTI. And then from that experience, they conceptualized GMRT, and the entire team of UTI radio telescope was, involved with the GMRT facility. That's what, it's doing translation. I was saying, I don't have that statement in my slide. Okay, so this is the Udaipur Solar Observatory Telescope. This is a new, half a meter off-axis telescope. This is an old facility which looks at full disk, and this looks at only a portion of the solar active region and so on. So that's also a combination which is required to observe sun, because we are getting more and more high resolution observation. High resolution will only allow you to look at portion of the sun. Active region, or even if you go to 4-meter telescope, you will not even see a full active region. You'll see only a sunspot. The other sunspot cannot be seen. So that means, you don't know what is happening in other part of the sun. So it is important to have a full disk observation as well. A combination of full disk and a high resolution telescope is most ideal. And we are working towards that for future things. So this is currently, this is the largest optical facility from India in terms of solar observation. So this is a 50 centimeter off-axis, aims to obtain accurate polarimetry with high spatial resolution. This was again built by the same company who built the 3.6 meter Devasthal optical telescope and the 4-meter liquid mirror telescope, AMOS. This is the same Belgian company who built this. In fact, the new 2.6 meter telescope, which is there in Mount Abu, which PRL has constructed, is also built by AMOS. AMOS is having good business in India. So polarimetry is crucial, because that allows you to get an estimate about the magnetic field in the solar atmosphere. Traditionally, we were using, Zeeman effect concept to measure the, magnetic field on the surface of the sun. So photospheric magnetic field, by now, I hope, you have a concept of different layers of the atmosphere of the sun. The visible surface is called the photosphere. But then if you go higher up in the atmosphere, your emission strength also weakens, and Zeeman effect becomes, even less prominent. And also because of, you need to have a line, a spectral line, which will show you splitting and so on. So the other alternative is spectropolarimetry. So polarimetry gives you all the Stokes parameters, and from there you can get an estimate about the field. You can get a direction and so on. So spectropolarimetry is the key for future, solar magnetic field observation. It also has a narrowband imager. There are again two wavelength, one at photospheric height, one at chromospheric height, looking at. And this is the polarimeter which I was talking about. They're also planning to have a multi-slit spectropolarimeter. This is very similar to multi-slit experiment which we are going to do from Aditya also, which I hope to present after the tea break. So that's the telescope there. For solar observation, the main problem is we have too much photons. For nighttime, it is just the opposite. They lack photons and we have too much photons. So how to, and it generates a lot of heat. That heat will again disturb your, optical quality within the telescope. So how to manage this heat is the main problem. So you see here, there is a hole and then a sort of, sheet of, it's not a paper, but it's a big sheet, which is sort of, trying to protect some sunlight getting into the telescope and so on. And it's in the open. So this is again, another issue is that when you have a telescope inside a dome, then inside the dome, you will have lot of thermal, distribution, and that creates again a lot of local turbulence, and that distorts your image quality. So for solar observation, now we are going into an open dome concept, so that there's a strong wind, and that will take care of the local turbulence which is there in the vicinity of the telescope. So the dome wise also, there is a huge difference now in the dome design of a nighttime telescope and a daytime telescope. Again, this is our favorite Kodaikanal Observatory of Indian Institute of Astrophysics, located in the beautiful Palani range. Some of you have spent time, I understand, there. It was established in 1899 as a solar physics observatory, and all the activities of Madras Observatory were shifted to Kodaikanal. So, of course, the Britishers made a Madras Observatory even 50 years back to 1899, but Madras is even terrible for doing astronomy. So they moved to Kodaikanal, but Kodaikanal also has its own problem, as Nainital has. It heavily gets affected by monsoon. And unfortunately, because of whatever industrialization and construction we have done, we have spoiled the climate locally at least, and the weather really goes bad later in the day. So morning hours are still okay for solar observations, but late hours is terrible. So you really need to go higher and higher altitude mountains, and we are trying to build a facility in Ladakh area. So, but again, Kodaikanal has a few facilities. It has again a H-alpha telescope. It has a white light and calcium and other filters you can load on that. And there is a twin telescope which is looking at again calcium and white light. And of course, it has more than 100-year-old library. This is one of the oldest libraries in Asia. It has the first volume of Aditya-L1 also in that library. So it's again a archival place as well. And I will talk about this data which we have digitized. And if you go back to 1st January 58, you will see there is a multi-wavelength observation available now from the digital archive. But before I go, this is the future which we are working on. This is a lake called Pangong Lake. I guess most of you have seen 3 Idiots last scene. And this was shot somewhere near this location. And this is our tower there. You could see we have an intrusion in the lake. This lake is 130 kilometers long. 2/3 is in China. And probably you have heard all the news that there were some people trying to get in here. That's a sensitive area and we have issues, but we have acquired the land. And you can see that small little hut, and this is a small little Maruti car going towards this. I have spent a couple of winters, 2 weeks. We are not allowed to stay more than 10 days at a time. This is 14,000 feet and above, but the sky is fantastic there because you are devoid of any monsoon or anything. It's a cold desert, and once it is clear means the whole day it is clear. It's not like afternoon it becomes. That's again another big advantage. You have long chunk of hours of observation. So this is quite a tall 5-story building. You can see if you go to Devasal on Sunday, you will see similar structure which we are planning here, about 25 meters height. Why we need such a telescope? Because as I was indicating that at least 2-meter class telescope, if it is there, so we are projecting a 2-meter class. So you see the jump from 0.5 meter size to 2 meter. It's a big jump in terms of solar ground-based facilities for high resolution observation. Currently, these are the telescope which is available in the globe. Gregor is a 1.5 meter telescope, which is just recently been upgraded. It's in La Palma here. Then you have Goody Solar Telescope, 1.6 meter in Big Bear Solar Observatory somewhere there. And then Decast, this is the largest solar telescope, which has been still in, I would say, not fully functional mode, in the sense one by one instrument are getting making available there. In fact, I don't know, Krishna has a observing time. He's waiting for the run. This is the largest optical telescope from the ground, a 4-meter class. And we are planning NLST here. So you could see how nicely it fills the longitudinal gap, because these people will be sleeping when sun is up there. So it is a very, very important project in global scenario as well. And as you can see, even say GMRT, how we were just was mentioning about this pulsar timing array. It's important that you have directions in all locations from the globe. That's why India is part of SKA. That's why India is part of India LIGO project. So solar, we cannot fall behind. So hopefully we will have NLST, National Large Solar Telescope, for you people to enjoy. We will just get the funding ready. So that's the location of NLST, filling the data gap. Now I will go back to history, and we'll talk about how Galilei started looking at the sun, that more than 400 years back. And this is his hand drawing. So it was just about 1600 when the telescope was sort of discovered, and then Galileo started looking at many objects, and sun was no different. There are certain myths, but don't go by that. So, Galileo was not so foolish to look at the sun and lose his eyes. So there are myths that Galileo lost his eyesight because he was looking at the sun, which he should not do anyway. But it is just a reflected light which he projected on a piece of paper, and that's his hand drawing of the location of the sunspot. So what he noticed, that there are certain regions on the sun with such black spots. Of course, he didn't know that they were magnetic in nature, but his observation was that he noted that that particular object, next day if I look at, it is towards the right. It's not always in the same location subsequent days and all that. From that, he conjectured or inferred that sun is a rotating sphere. Of course, he did not know the sun is not a rigid body, and it is not rotating as a rigid body rotation, but he could make out that sun is rotating at its own axis. And this is just an animation made out of his, his drawing. Of course, north is here. We have to correct for this north-south direction alignment depending on which place in the earth you are doing and season and so on. So just be aware that the sunspots are located in a belt here. This is say 1 month of data, and so then you can make out that this is the pole, North Pole, and this is the South Pole. So the sunspots are only restricted to a certain latitude band also. This will be a very important information for our subsequent thing. So if I look at the sun someday, it is very boring. Nothing much is seen. But then certain days you will find these spots. These are called sunspots. They often come, not often, they will mostly come in pairs. And if I now look at a little more closely with a better telescope, I will look at these objects even more details. This is the sunspot pair. This is called umbra, and this surrounding area is called penumbra. You can make out that the umbra is more vertical magnetic field structure, more concentrated. Probably strength is also more, and this is called penumbra. The umbra is the location where the strongest magnetic field is there. It is dark because it is not allowing the energy to efficiently come from below. So that's why it is dark. It is also cooler than the surrounding. That also makes it darker. And the surrounding region, penumbra, is more like a filigree filament kind of structures here. And it already appears from here that they're probably more horizontal in nature as compared to the umbra here. But now there are certain properties of these sunspot pairs which we need to worry about. How these sunspots come in the first place. So now we understand these sunspots are probably like these magnetic flux tubes. Flux tubes are nothing but composed of millions of magnetic field lines. And these magnetic flux tubes are lighter than the surrounding because of magnetic buoyancy. I'm actually jumping a little bit, but I guess some of you are already aware, but you will have a hydrodynamic at MHD class. There you will see what is precisely magnetic buoyancy. You have heard more about plasma beta and all that. So all that makes the flux tubes lighter than the surrounding, and then they come from the bottom of the convection zone. And when they come up, so here you see that these flux tubes are coming up. One will give rise to one polarity, and then the other one will give to another polarity. And if these tubes go up, and then if certain rotation or certain instabilities will sort of make these kind of effects, this is called magnetic reconnection. They're forced to come closer, and then whatever material was confined within this tube is ejected into the interplanetary space. You have the storm. So this is called the origin of the solar storm in a very nutshell. So this is what is magnetic buoyancy explained here. So typically, in the base of the convection zone, the flux tubes are originated. That's what is the current understanding. And then once you start a little bit of push here, the tension doesn't allow you to the tube to come up. It's like a rubber tube, you can imagine. If you stretch the rubber tube and hold it like this, but then if somebody pulls it, and if the buoyancy is so it's a interplay between different forces which is acting on it, and then finally it emerges in the photosphere, and the pair of sunspots are generated. Of course, the slides will be and the recordings will be all available for you people. So please look at the slides, and you can ask questions later on. I'm not going into the full mathematical details of these things because of the disbalance of different people coming from different background. But if you are interested, we'll be happy to give you the the mathematical details of this. So let's look at some of the properties of a sunspot pair, because from the theory, we have to be able to explain these properties. And the properties are accumulated or sort of collected by looking at observations, at a single day and all over for last 100 years. So here you see, again, a sunspot pair. This is taken from a Hinode spacecraft. And those sunspot numbers, if I plot over last 400 years, I see this periodic variation. There is alternate peaks of solar activity. Sometimes there are lots of sunspots, which is called maxima, and there are period over, there are only very few sunspots, or sometimes there are no sunspots at all. There is a mystery from 1650 to 1700. There were no sunspots recorded at all. So now Maunder discovered this. That's why it's called Maunder minima. And we still do not understand completely what went wrong in the sun, that it was not producing any sunspots. There are certain theories now. These are called grand minima, and there are people who work on this for last several thousands of years, and it's been predicted probably there were 22 or 23 such grand minima in the past. And these are actually mini ice ages. What happened was, during the solar Maunder minima, the Volga River was frozen for 30 years. It was extremely cold in Europe. Several thousands of people died during that period because of cold alone. So this is not affordable in the modern day. Of course, it can compensate a little bit of global warming, but this balance is not something which is affordable. So we need to understand the solar cycle and whether there is any such possibility of a big minima or big maxima. And as you can see here, last 100 years of cycle, saying that this cycle was much stronger as compared to all other cycles. So if this cycle again repeats, means there will be lots of solar storms. And lots of solar storms means a lot of satellites will be destroyed. Just one thing. There are other effects which I will be talking about briefly. That's an area called space weather. So it is not desirable to have a situation like this or this as well. So it is important to be able to predict solar cycle behavior. These are long-term behavioral change, and also there are some certain things called short-term behavioral change, like whether there is going to be a solar storm tomorrow or not. One thing is that next 5 years we will have hundreds of solar storms or thousands of solar storms. That's one prediction. The other prediction is it is going to be today or tomorrow. It's like, you know, every day we are getting SMS that the thunderstorm, but nahi ho raha hai. So ye bhi problem hai. So weather prediction is still in a, you know, really bad shape in the country, it looks like. But I must say, you know, in the West, it is much better. They are able to do it at least 6 hours in advance, pretty well. Jolly well, I would say. I was just last week there also, it was matching. So we have to do a lot of work for weather prediction. Weather prediction demands a lot of data assimilation, but the data has to be collected also in the right time. If you have a old data that if you feed it to the computer, it will not be able to, because these are not linear systems, these are non-linear systems. So it is not possible to predict actually very well in advance. So timing is very important. So machine learning is the key. I mean, there is no way you can avoid that. But again, machine has to be trained by humans. So if the training is not good, machine will give you wrong results. So that's what is happening now. And it's our job to train the machine with better precision and better quality of data. So again, another interesting fact is Samuel Swabe, you see, he observed for this period, these two vertical lines. So already he saw this and he predicted the solar cycle. See, this is the thing about the old scientists. They could see some, you know, indication, and they were able to predict that there is a solar cycle. I do not know, because it's 2.5 cycle probably, right? So from there itself, you know, Swabe said, so that's why often it is called Swabe cycle as well. Now, if I now come back to this, so that was the why, you know, basically that was the G-band picture. And this is a magnetogram, which provides you the information about the magnetic field, the strength, and also the direction here. You could see the arrows gives you the direction, and also the vectors gives you indication about the flow velocities. How, you know, how much flow is there, but the length of the arrow, you can measure direction and the strength of the flow as well. So there is always an angle between this sunspot pair. This is called the tilt. And this tilt is also not always same. When a sunspot pair appears in certain time, there is a tilt, and that tilt changes with the solar cycle as well. So one needs to be able to explain why there is a tilt. So if I look back at the full disk magnetogram, so here you see that sunspots are pair always. They are called active region. You have heard 2 color polarities are indicated here. Active regions have systematic tilt, which increases with latitude. So here the tilt is in this direction. The higher you find the sunspot pair, the tilt is more. When they are appearing in a lower latitude, closer to the equator, the tilt is less. And the tilt is this way in the northern hemisphere, and tilt is ulta in the southern hemisphere. And also, if you see the polarity, the yellow guys is right side of the blue fellows here, of the green fellows here. In the southern hemisphere, it's just the opposite. So the polarity is also. So the polarity orientation is opposite to the 2 hemispheres as well. So my point is, we are just first trying to show you what are the observational facts which need to be explained by when you make a theory. So I understand I had not looked at Gopal's dynamo equations. Probably he didn't explain the dynamo theory in terms of explaining all these observations, right? Okay, so okay, probably there could be some repetition, but it's okay. So here, this is what is sunspot cycle. So in the initial phase of the solar cycle, the sunspot appears in the higher latitude, and with the progression of the solar cycle, the sunspots appear more closer to the equator. And if you plot it in time-wise, then what you get is called the butterfly diagram. So this is what is called butterfly diagram, and we need to be able to explain this. So this is again a continuum image from HMI. These are called bipolar magnetic regions, as you see here. Yeah, you can use this here as well. And there is a tilt, which needs to be also explained. This is the angle, and this is the other polarity. As I said, the tilt is in the opposite way it is detected. Now, that was the butterfly diagram of the white light sunspots as has been observed. Now, if I look at the magnetograms, and now these magnetograms, if I now, make animations and then open it in this form, this is called the magnetic butterfly diagram. And as you can see here, that the beginning of the cycle, there are lots of sunspots pairs and they appear in the higher latitude, but then with the solar minima, this is going more closer to the equator. And then again, in the beginning of the solar next cycle, it is appearing in the above region and so on. So these are called Carrington maps. So the Carrington maps are global representation of the evolution of the magnetic structures or sunspots or other elements. I will show you butterfly or Carrington maps of features as identified in calcium or H alpha as well later on. So you see that these things are now here projected from 1975 for 20. I mean, this is up to the last few years, and then what you notice here is that the major polarity moves towards the equator, but you also see the receding polarity goes towards the pole. And here there is also another thing to be noted here is the northern hemisphere has a yellow one polarity and the southern hemisphere has other polarity. But every 11 years, this polarity, the magnetic polarity of the hemisphere also changes. So this is called polarity reversal. So if I have a dipole, I mean, if you just assume very, to make it life very simplified, if I assume that there is a dipole inside the sun, then if the dipole, the north pole of the magnet is facing toward the northern hemisphere, that flips. Every 11 years, that flips. Of course, it's just not a simple magnet. So, but then if the sun is a completely convective shell, it's a big ball, then you have to be able to explain why this magnetic polarity reversal happens. So it's just not enough to be able to explain this movement of major polarity towards equator, and then getting during the minima period, what you are seeing is that the yellow guys are going to the equator, the blue fellows are coming here, they cancel each other. You have solar minima, you hardly have any sunspot. But during that minima phase, actually the polarity reversal is happening. And then here what is happening is this slowly these blue guys are going, they are interacting with the pre-existing yellow fellows, and slowly the yellow fellows are all eaten up. And then the polarity of the hemisphere or the northern hemisphere has become blue now. And exactly the same thing repeats again in the next cycle and so on. So the solar cycle is actually 22 years because it has 11 years of sunspot number cycle and also the polarity reversal. So if you want to take these two together, then you have to be able to explain this 22-year behavior. So this is again a majority has to be explained by any theory, which is now invoked as a dynamo working inside the sun. And here we create the Carrington map by looking at these everyday magnetograms and then chopping it over. It's like opening it up and forming it in this 360-degree fashion here. The other thing to be noted here is that we do not have any synoptic or detailed magnetic field measurements available before early 70s. So that's again a huge problem to understand the magnetic behavior of the sun, because the magnetic measurements are not available. So that means you have to look for proxies, which represents the magnetic field. Of course, sunspots do represent magnetic field, whether 1-to-1 or so, we have to work out. There are other features in the sun. We have heard about plages, so there were some questions on that. So plages are the regions surrounding a sunspot, which represents or which corresponds to slightly weaker magnetic field than kilogauss field in the sunspot, as Krishna pointed out yesterday. And also you have these filaments. These are huge structures or prominences. They call prominences when they are seen outside the limb. When they're seen on disk, they are called filaments. And those are also, representing magnetic location. How they are, I will come back to that. So combining all that information of calcium images, filament images, and sunspot images, we have to build this magnetic field map for the past century. That is what we are doing actually these days. So this is again, David Hathaway has been working on this stuff for ages, and he created this movie. So the most visible thing is, as I indicated already, equatorward migration of active regions, poleward migration of the decayed diffuse field, and polar field reversal at the maximum of the cycle. So all these properties has to be explained by a theory, which I will invoke. What we understand, I think Gopal has given you this description, but I'm just giving you more in a phenomenological way, just to keep the basic ingredient in mind. But if you want to really do a proper job, you have to write down the equation, then you have to solve the dynamo equations and so on. But basic concept is that sun starts with a poloidal field, at theta plane, and that poloidal field has to somehow get converted into toroidal field, and the toroidal field has to again feed back to the poloidal field, because you have to explain a cycle. So you have to invoke a theory which has a cyclic behavior. One is feeding the other with a certain periodicity. So that's the concept you have to bring in. So how do you get toroidal field? What you start with is a poloidal field. As I was saying, you can simply assume a north-south oriented field, and then sun doesn't rotate uniformly, sun rotates differentially. I did not talk about it too much, but I guess one of your interior class had seen that the equator rotates much faster than the pole, and that will basically will stretch your north-south poloidal field and will create this toroidal field, and then the toroidal fields, when it it degenerates, then the sunspots appear in the surface, and as I indicated, these sunspots when they appear, the plus guys here, just one representative examples, with the progression of the solar cycle is moving towards the equator. The negative fellows are moving towards the pole, but the pre-existing polarity is plus here. So they will slowly, there is a process called Babcock-Clayton. I will explain a little bit more. And once the polarity reversal happens, these polar fields is dragged to the base of the convection zone, and that becomes a seed field for the next cycle. So you have to have a cycle. So from initially poloidal field, you get a toroidal field. Toroidal field gives, through the Babcock-Clayton process, is responsible for the polarity reversal, and the polar field that is dragged to the base of the convection zone by a conveyor belt. I will come to that. And then that becomes the seed field for the next cycle. So that's the cycle. So all these processes, the time scales of these migrations will dictate what will be the periodicity. And if this process is faster, and if you have more sunspots or faster polarity, reversals and so on, you can imagine that the next cycle will also be probably stronger and may come earlier as well, because there is a push in the earlier cycle. So it has a history. So we can predict a solar cycle only half a cycle in advance. So that's also roughly is the current understanding. So as I was indicating, so how do you get the toroidal field? Basically, also you need turbulence inside the convection zone, and this turbulence diffusivity, this is again another very important parameter in the dynamo, which will again dictate the how efficient these flux tubes are coming to the surface, how fast it is coming and all that. So that's term called diffusivity. In fact, the dynamo, the same model will predict a completely different cycle strength for the next cycle, depending on how how you choose the diffusivity parameter. And in fact, happened in the past. I will not go into the history, but that really one person predicted a very strong cycle, and one person said that the cycle will be moderate, just because of they use a different diffusivity in their simulation. The other important parameter is called meridional flow. As I mentioned, it is like a conveyor belt. So as you see here, so there is a flow pattern on the surface, and then that is dragged to the base of the convection zone. So these meridional flow essentially dictates that the decaying active region, how this diffuse field is dragged to the poles, how fast it is dragged to the poles, and then how it is taken to the base of the convection zone will depend on this, speed of the conveyor belt. It is like, I say that in the airport you arrive, your bag is not delivered because the conveyor belt is too slow or it's not working. So there is a hypothesis that it's the main culprit was the meridional flow in the Maunder minima period. Either the flow was somehow get badly affected, and there is also another theory that probably there were sunspots generated, but the sunspots were far too small. Because today we have modern telescope, we can measure big ones and small ones. But in 1600, the 4-inch telescope were not able to see the small guys, and they were omitted because dynamo cannot stop. I mean, it is impossible to, because sun still rotates and sun has convection zone. It's in the main sequence for last, millions of years. So that is the only way people explain the Maunder minimum. So this is the sunspot number. But in modern day, what we are doing is, we are actually, this is my students' work. Sudeep did from Kodaikanal white light thing, and we generated this cycle. But we are actually now showing more as sunspot area, because area is a better representation of a magnetic flux than the number. Because you may have small, sunspots many, but a few big guys will be equivalent to small many. So we are actually, sort of projecting this to the community, and this is being very well recognized also now. For a better magnetic proxy, it is probably better to have an area measurement. But of course, the problem is area measurement is not available before 100 years, simply because we didn't have the images. We had hand drawing and all that. Hand drawing, again, the plate scales and all that is, I mean, somebody takes a page of this size, somebody takes a A4 sheet, one takes a A3 sheet. It's completely gone because it's very hard to make a comparison between different, plate scale. You understand that, right? I hope. Okay, so so area information was not there for the many hundreds of years. It's only the sunspot number which is possible to be picked up from those drawings, which are of different sort of sizes and so on. And this is the butterfly diagram. You saw the first movie, which was actually done one more step, because now Sudeep went to Max Planck and he combined 13 observatory data all across the globe, whatever is available, and he cross-calibrated. This is what is, again, science-wise is very important. You have a data from this source, you have a data from this source. How do you know that this data can be really compared with this? So you need to cross-calibrate the data and then put them all into one, platform, and then you can do the, composite series. So he has produced this composite series of sunspot area, which is probably the state of the art now. So so here you could see we can have monthly average, we can have daily, and then again yearly average also. That allows you to do many more things you can imagine for the past history also. Although we are at the moment only looking at maximum monthly, not even daily thing. But with the more advanced machine learning and all that, probably we'll be able to, because it's all terabytes of data we are handling. So I have a 30 terabyte disk sitting here, and these people are working with those kind of data series. The other interesting aspect is, this is the polar field which is shown. So this is the sunspot area series, but this is the polar field. Now, as I indicated, during the minima, the reversal happens and the polar field becomes maximum. And this polar field becomes the seed field for the next cycle. So next cycle's strength is somewhat dictated by the polar field, how much it is generated. So this is exactly the opposite phase. You can see here that when the sunspot area is minimum, your polar field becomes maximum. And here, both the polarities are shown here. There are many more interesting thing happens, that polarity reversal doesn't happen always in the same time. It can happen that both the poles of the sun is having the same magnetic polarity. I mean, North Pole Geographic north has, say, magnetic north, and geographic south has also north, magnetic north. It can happen for a few months. And you can imagine what is this magnet all about. It's a summation over billions of magnets, if you think about in that way. So as you can see here, that it is not really perfectly symmetric as well. So we need to be able to reproduce all these things, and cycle to cycle also there is quite a bit of difference in the polar field behavior as well. So how the overall solar, this is again a global field I am talking about, right? This is not every sunspots or every active region's details. It is an average property of the sun itself has so much of variation. So it's still hard to explain everything, but there we are. So this is again a concept. These are slides from Vibhuti. So again, a repetition of what I was saying. During the minima, you have this poloidal field. Equator rotates faster than the poles. So that gives rise to, this toroidal field. And this toroidal field generates this sunspot. And here also you could see that this sunspot pair, the inclination is, opposite here. Because of the orientation of the magnetic field lines, the way it is wound, the north polarity is in the right of the left in the one hemisphere, and just opposite in the other hemisphere. It's again, this is depicted here because of the orientation of the toroidal field, how it is generated out of these poloidal field structures as well. And then, as I indicated, this conveyor belt, which is this meridional circulation, is taking this, decayed field to the pole, and this from the pole, this field is, dragged to the base of the convection zone, and that becomes the seed field for the next cycle. So that's the sort of overall scenario. This is the picture in the maxima. So there are actually, so that's why the dynamo is often called the alpha omega dynamo. Omega represents this differential rotation, and alpha represents how you describe the convection. So different stars can have, different profile for its convection or rotation. So depending on the rotation and the, convection numbers, the other stellar properties of the stellar cycles, whether it will have a shorter thing than 11 years or much longer, will all depend on what is the, numbers in this. But there can be also scenario where the convection is much more dominant than rotation. So in a fully convective stars, or when it is in a later stage and so on, then alpha is much more stronger. So then it will be called alpha square omega dynamo, right? So you can construct dynamo by playing around with this different parameters. Again, in the case of the Earth, polarity reversal, we don't know when it will happen. Again, it's millions of years probably it takes. So obviously convection is not so strong. I mean, we know that, and Earth doesn't rotate, thankfully, differentially as well. So, so that's again, a lot of cartoons you can have. You can see it from my slides. This represents the eddy structure of the convection. These are early theories of convection which has explained or given this number. And then you have this Babcock-Leighton process, which is again explained here, that you have this plus guys and the minus guys, plus fellows will move to the pole, and they will eat up slowly few negative fellows, and then eventually all become, during the minima, you have the strongest polar field, and you can see that these have cancelled each other. So you hardly have any sunspots during this period, during equatorial region, and then you have a beginning of the next cycle and so on. So, so this is again a animation which was done by Dibendu Nandi, who is in IISER Kolkata, and we have this meridional circulation, and then that creates the sunspot. So they have a little better. These are called kinematic dynamo models. Why they're kinematic? They're self-consistently not able to measure the velocity field. Convection is a least understood subject in physics. And we treat convection by different, approximations. Self-consistently, able to fully treat the convection demands magnetoconvection simulations, and that demands supercomputers. And even today's most modern supercomputers are not really able to really do the entire sun. They're able to do small portions of sunspots and all that. But having said that, there are pretty good advancements happening in stellar full MHD simulations. And they're able to generate solar cycles, not all the properties, but they're able to generate solar cycles. But the kinematic dynamos, which has certain approximations in terms of its velocity approximations and so on, but able to generate most of the solar cycle behaviors now. So a little bit of advertisement about the Kodaikanal archive. As I indicated, that we have more than 100 years of data from Kodaikanal. These are all in the public domain. And there are many publications from our group, other colleagues from India, and worldwide, because the data is public. There are Japanese, Russians, Americans, Europeans, everybody is working with the Kodaikanal data. Because as you can imagine, Kodaikanal Observatory, of course, we are taking the, sort of credit, but it was built by the Britishers, right? So, I mean, they had this vision of, doing modern day astronomy way back 100 years. But only good thing that we have been able to reproduce or sort of maintain that. And there is another interesting aspect about the Kodaikanal Data Archive is, see, we were poor, so we never changed any optics or anything. Kodaikanal did not have money to upgrade its, its telescopes and all that, but it only maintained the telescope and continuously observed with the same instrument for 100 years. That makes the Kodaikanal data most uniform data in the globe. Because in 60s and 70s, people have upgraded their, observations. So when you upgrade their observations, it is hard to compare with, older, observation setup and the current observation setup. There are a lot of calibrations are necessary. And they moved for high resolution. They were not looking at with this old telescopes and all that. So for the long-term study, beyond 70s, actually, the modern world neglected it. They were not interested in there were only very few people. But then when people started seeing that the digitized data is so rich, and there's no magnetic information before 70s in any case. So you need to go back to the historical data to have an artificial way of generating this magnetic information. Without the magnetic information, nothing is explainable. So in principle, actually, modern day astronomy also everywhere, it needs magnetic field, but people do not know how to treat magnetic field. Even you will be doing black hole physics and jets without magnetic field. But that's the state of affair, because it's much more harder to include another vector field in your equations. But be aware, 20 years down the line, no papers will be accepted without including magnetic field, even in majority of the astrophysical scenarios as well. So I have too many slides from this, so maybe I will have to skip few and show you some. When I'm in Zoom, I cannot choose it online. That's a problem. Okay, so that's the sunspot area series which I was talking about. Now, as I indicated, so Shudip has been able to reproduce this from the earliest data which was available for sunspot area from 1870 odd, and he has produced this butterfly diagram. This is quite beautiful. The other thing which we are actually very highly looking at is different sizes of this sunspot. So what is shown here is the biggest guys are represented by red, and then progressively you have the green ones and the yellow ones and the blue ones. As you can see that the small guys are only available in the high latitudes, right? Whereas the red fellows are only there with the low latitude, and during the maxima, nearer the maxima phase, only you see these big fellows, not throughout the solar cycle. So major space weather effects will actually come from the big active regions, not from the small ones. Normally, there could be exceptions. And these are, and the blue fellows are actually there everywhere. Of course, it looks like it is a periphery, but they are there everywhere because it's superposed. So is it that the small guys are generated from the same dynamo mechanism? or the small fellows are generated throughout the solar cycle by a different mechanism. So there is now a concept of a local dynamo versus the global dynamo. So maybe there is another mechanism which is happening just beneath the solar surface, which is responsible for small flux tubes or small magnetic field generation throughout the cycle. Because during the quiet phase also, sun is very hot, as you know, and these I did not talk about it at all. There are small flux tubes everywhere in the sun, which is of 100-kilometer size, everywhere on the sun. So the salt and pepper is there everywhere. It's a big active regions there in certain places and only in certain points. But the small flux concentrations are there throughout the sun, everywhere, at any phase. So what is responsible for generation of those? So that's why there is a new, new paradigm coming about the generation of these small flux concentrations by a local dynamo. Then another option is it that the big guys can, get broken into small fellows, or the small fellows march together and becoming a big fellows? So there are all these, different possibilities. And again, machines has to dictate this finally, because there are billions of now magnetic flux concentrations we are talking about, not one or two. So really, to do a detailed job of these small guys, we need really high performance computing. And that can happen only if we are able to train the machine appropriately to come out with this here. Because we select certain samples and do the analysis and all that. But eventually, I think all these will demand. Then there is also many important area. The two hemispheres is not always same at all. I've been talking about sun as a global thing, but the northern hemisphere doesn't behave the same way as southern hemisphere. There are a lot of differences in northern hemisphere and the southern hemisphere. There are asymmetries. So how do you measure these asymmetries? How do you quantify these asymmetries? And as I just indicated, even the polarity reversal doesn't happen at the same time. That essentially proves that the two hemispheres are not symmetric. So all these, so many new properties we are able to now identify that to explain them. But again, these properties has to be quantified by a very rigorous data analysis. Otherwise, whatever theory we are trying to generate will be, not reproducing the same thing. So first is, observationally, what needs to be explained has to be generated, and then theory has to be developed. So here, sometimes it happens, theory goes ahead of observation, but in this particular case, it appears that we are ahead. I mean, we are compiling the data much more. I will just, ignore this. There are n number of work which we are doing. This is called calcium. Calcium is looking at the chromosphere. This has been recorded again with the same, setup as I indicated for last 100 years almost. Calcium becomes a very good proxy for magnetic field, because as you can see here, this is just a very archived image. The quality you can make out from, how difficult it is. See, there are two little dots here on the one side and this side. That is actually hand marked by North Pole or South Pole. So we have to fit this image. We have to identify where these dots are and then rotate this image. There are lots of steps required when we are doing digitally processing. I hear you do everything manually, but we don't. So even this single dot and double dot is identified by a computer program where it is. But first you have to identify where the solar limb is, because this is not symmetric, right? This image is not symmetric in the plate. So there are a lot of states. So we apply a lot of mathematical operations. They called Hoff transforms and so on, which will identify where your limb is. Then you center that. Then you have to put coordinates, because this is only 4K by 4K CCD image, right? Majority is junk actually. We don't need the other portion. So we have to only we are interested only in the solar disk. So to extract just the first phase itself, students spend years to get the clean data. Then only the the science starts. So computer programs are very, very crucial in this. We did digitize this with a CCD camera, with a 4K by 4K thing. The camera itself costed about 1 crore. So this was one of the best digital program, actually digitization program in the globe, I would say. So this is sort of statistics. Very quickly, I'm showing. So typically, you will have, for last 100 years, some days you will have multiple images and all that. And as you can see here, 1957, somehow there were more observations. We were interestingly there in 50s there was a year of International Geophysical Year, IGY, and all across the globe, the observatories, they collaborated in 50s, 57. And that's why they were campaign mode observations. I was surprised कि suddenly in 50s इतने data कहाँ से आ गया, बाकी time में क्यों नहीं है? Then of course, because of the coordinated observation, there was special mode of observations and all that. But of course, certain times you have data gaps, and as you can see here, closer it is. I do not know. There are two reasons. One is that we are becoming more lazy. The other is that the weather, we can blame for it. So it appears that, our predecessors were much more sincere. Every day morning, irrespective of whether it's good or bad, they were opening the telescope and observing. Here we are looking at the forecast. और SMS आ गया तो नहीं जाते हैं. So I think it makes a thing. Then I will show you. So that's the calcium. We have produced calcium butterfly diagram. This is 3D butterfly diagram. This was produced by Shubhamoy, my former MTech PhD student. Shubhamoy did two jobs in his PhD. His PhD was to design the optical design of suit instrument, which you will hear in the afternoon. One of the payloads in. So he initially started his work with suit, but as it happens, Aditya was taking its own sweet time to complete, but he has to submit his thesis. So I gave him Kodaikanal data, which was not part of his thesis at all, but he was brilliant mathematician also. I don't know how he went into engineering. So whatever tools I asked him to develop, he coded that, and he could do this. So so the entire calcium series calibration, and then identifying the plages area, where how big, and so here also you see the big plages versus the small plages we have. That is indicative of the active magnetic regions. And here he produced the magnetic butterfly diagram. I think this was the first 3D rendering of butterfly diagram, and that. In fact, he did two work in the PhD thesis, but then this has fetched him the postdoc, and last year in Nature Astronomy also. So he's completely into machine learning, and he's looking at magnetogram images, and he's predicting the magnetic field, how the active region will, be, and so on. So he has a 3 author Nature Astronomy. Normally, you will see 20, 30 authors in a Nature Astronomy paper, but he's the lead author with his boss in Boulder. The other thing, as I indicated, that the same object, when you look at disk, they will be called filament, and in the offline, they will be called prominences, but the object is the same. These are magnetic clouds, comparably colder structures. But what we understand is that they also gives you a location where the magnetic polarity inversion line is. You have two opposite polarities on the two sides, and this material is actually floating along the magnetic polarity inversion line. So that really gives a very good indication. Directly, it is not giving magnetic field where it is located, but now you look at calcium, look at where the sunspots are, and look at where the polarity inversion line is. So by combining all this information, can you produce the magnetic field map? So that's what we, some of us do. So this is, a comparison again. This is a calcium, and this is the H-alpha. So H-alpha, of course, is showing those patches also, but these are the filaments. Basically, these filaments are along the polarity inversion line. So always you will not find so much of magnetic field concentrations in the calcium, or definitely not in the sunspot white light images. But you will find many more these filaments, because smaller fields are also there. As I indicated, the smaller fields are not been captured well by, definitely not white light, to some extent by calcium, but really H-alpha is providing you locations of polarity inversion line in many more locations, all the way to the poles also. The other very important element is that sunspot only appear 35 to 40 degree latitude. But we need magnetic field everywhere. So only H-alpha and calcium somehow is giving you information about higher latitudes. No information is possible from sunspots, because sunspots do not appear more than 35, 40 degree latitude. So that is why this calcium and H-alpha data becomes very, very important resources. People were not able to do it earlier, but now with, with all these new data which we are generating, this is H-alpha archive. This is global scenario, and you see Meadow is one observatory where they have H-alpha information, but these are not in digital form. In fact, I had a IU symposium organized in India a few years back, and global people came, and they were not getting funding for digitization. And I hear last year that they got the funding by showing our results, that how digitization is helping, this thing. So Meadow data, we have, they have JPEG images, which we are also using it. But all these are in the digital form, means it has all fits images with the full header information and all that. It has much more information in terms of if you want to really do proper science with that. Whereas some of these images are in the JPEG form. I mean, it's good for image, but to do real high quality science, it's harder. So that's the sort of global scenario. Again, Kodaikanal is probably one of the best resource for this. Let me, we are eating into, so this is one plot which I will like to show you. This we have reproduced the magnetic, for the last 4 cycles, we have produced the magnetogram. These are called pseudo magnetogram. They're not real magnetogram, but from, as I indicated, from all these other, data from H-alpha and calcium, we have been able to produce this. This is a work with the Russians and our colleagues from IIT BHU. We have been able to produce this magnetogram. These are first of its kind. The other thing which I want to show you is this source, which currently 2 students are working here. These are hand drawings. These are hand drawn, so this guy has worked on it. But the beauty is that in the hand drawn thing, people have marked by this. But the problem is there are a lot of junk on the outside. So he has a tedious job of counting this and doing it by hand, apparently. But we have this 100 years data now, and some of my students are doing with the machine. So these features are being identified, and then we will have properties, how, what is the area of the, say, these are filaments. These are also, the beauty is that the filaments are marked with one color pencil. These are marked with another color pencil. So you can use RGB criteria and so on. There is some K-bin clustering things and all that they have done. So we have now results from this. This has come, one result has come in UpJ. So we produced just 2 cycles, and the beauty is that you are able to see these poleward migrations, right? Which is not possible to be seen from sunspot data alone. So from the filament sun chart, of course, we have done this previously from digital also, digitized images, but the digitized images has certain data gaps and all that. The drawings are still there. They're in books, volumes. So some bad data, because of preservation and all that, produces data gaps. So we are hoping that the data gaps will be filled by this sun charts. And again, this is a good project for machine learning demonstration also, how machine does the job. And so then we can compare with other results and so on. So I think that's what, so again, this is the archive you can refer to. This is the team who has been involved, which was started with, Professor Singh and Ravindra, my colleague here, with whom he has done the project work. These are all old team members. The new team members are not here because they're primarily from IA. This data archive was built with Ayuka's help also, with NKN as a national project. And now I'm sitting here. You may not be able to see this view when you go on Sunday, but this is taken near Devasthalas only. Thank you for your attention.
Good morning, sir. So you said ground-based data and space-based data are both necessary to get good observations. And even after we are sending such good spacecrafts to take the observation, why is ground-based data still necessary?
Okay. There are two things. One is the space-based data. Space-based, first of all, telescope, the real estate is limited. Real estate means, how big you can build a telescope there. So the biggest telescope we have is a 20 centimeter. Having said that, in Aditya, but in there was a 0.5 meter telescope which the Japanese sent and all that, which did give you a good high resolution thing. But from the ground, you are able to build 4 meter class telescope.
Yes, sir.
That is not possible from space. So if you really want to go high resolution, then ground is the only possibility. And any instrument you make, as I said, real estate, the energy, as a power source, what you can use. A spectrograph itself is very heavy. The minimum size of it's a luxury. In Aditya, we have got a 175 kg. In the Western world, proposal would have been thrown into bin. Because the maximum weight they allow is each instrument, 30 kg, 40 kg, like that. So it is very heavy. So the spectropolarimetric experiment from space is very limited. There have been attempts, as I said, 0.5 meter telescope was there in Hinode, Japanese satellite.
Yes, sir.
But they tried to push for 1 meter class. It was not accepted. They got a UV spectrograph alone. That again gives you. Having said that, so the balance what people try to think is, see, the other wavelength, the shorter wavelength are not seen from the ground at all. So it is better to, use the space platform for, say, X-ray and UV and so on. The shorter wavelength, which you cannot observe from the ground. So the optical wavelengths and high resolution, you focus from the ground. And which also needs lots of data. See, for Aditya mission, the main problem for us is how much data we can download. Because we are going to a Lagrangian 1.1 like 27,000 kilometers. We have, only 12 times in a day we'll see the satellite. So we can only download certain hundreds of GB max. Yes, the decreased per hour it generates few terabytes. Per hour it generates few terabytes. So you cannot take that many images in the space platform at all. So if you want to go for high resolution, high time cadence, because solar observation, as I said, we have many photons. We are able to take, hundreds of frames per second. It's very different from astronomy, other research. So the exposure time which is possible is 5 milliseconds in the modern cameras. So that means, you have so much of data collection possible. So this is impossible from, space platform at all. So you have to judiciously, plan your observation on certain wavelength and certain modes for low cadence, medium resolution and all that from space, and ground with the high resolution and high cadence, high magnetic field, spectral information, all these from the ground. So that's the sort of, modern way of going about it.
Also, sir, we talked about the grand minima and the Maunder minima. So what are the theories behind the creation of the minimas? And will there be any events that may be like the grand maxima?
Yeah. Both are good questions. So one thing is, it's again, bit on a speculation and bit on the simulation, how you feed. As I said, simulation, the machine will only run it the way the parameters you feed. So people play around with parameters. And what they have shown that if you for some reason, there are, you see, differential rotation, if you could just change a little bit, if you could change the meridional circulation a little bit, what effect you see. And by doing that, they have been able to reproduce. Now, the question is why the meridional circulation will slow down? Nobody has an answer to that. Why the sun will rotate slightly slow? Is there some other planet which has come nearby or something which is slowing down? Some other object? Nobody knows. So this becomes a speculation, but theorists will only generate the theory that if this has happened, then it is able to explain the, these grand minima. So grand maxima means, there are certain, it is true that there are, but people still do not know grand maxima, what effect could have been, because there's sporadic, big flares and all that has been seen. Even there is a huge thing. And that will lead to a lot of flares and all that. Since you asked this question, there is a famous paper in Nature and all that about super flares. That if you have such huge active region, you will have big flares also. And super flares in other stars have been now observed. This is from, Shibata, Japanese group has done quite a bit of work. And if a super flare happens in the sun, what could be the damage? How many billions you will lose and all that? There's speculations are also there.
Okay, so final question. We are talking about the meridional flow taking the sunspots of different polarities to different regions. Is the meridional
not different region? It will only take one to the pole,
poles
because there is a
and
direction of the meridional flow.
Yes, sir.
Yeah.
Is the meridional flow like is it governed by the magnetic field? Like, is the meridional flow, is there a magnetic field along the meridional flow, or is it just mass transfer?
Yeah. So as it is understood now, there is no real magnetic field alignment along the magnetic, meridional flow. It is primarily governed by the convection. In the convection zone, how the, internal differential rotation. You see, we are talking about differential rotation, and on average, I've said that equator rotating faster and all that. The differential rotation profile inside is again different, slightly. So a combination of these two dictates what will be the meridional flow. Now, since you asked this question, these are again unsolved problems. How many cells we have inside? Is it one big cell, which is shown in the picture, or there are multiple cells? So this still we do not have a clarity on this. There have been results from helioseismology. We didn't talk about helioseismology. You mentioned about helioseismology. Gopal mentioned about helioseismology. So from the helioseismology results, we talk about, internal rotation, internal, density profiles, base of the convection on where it is, thickness of the, tachocline. So all these will, somewhat be crucial to understand these, real pattern of the meridional flow and what is the speed of the meridional flow. Again, it's all, some measurements are there because it's few meters per second. Because it takes years to go up there. So it's not very fast, you can imagine. If it is very fast, then of course cycle will be much shorter. Okay.
So
So when you say magnetogram, right, what kind of magnetic field does it measure? Like, is it like line of sight, if I'm not wrong, right? So how do we work with it?
Yeah. So the magnetogram images, mostly what I showed you was line of sight magnetogram. You are right. It's only one of the, if you do the Stokes vector, thing, it's only one component it is measuring. But now we have possibility of vector magnetic field measurement also. But the vector magnetic field measurement is restricted not to the full disk. It is done only with a smaller portion of the sun. Having said that, there are vector field also possible for full disk from SDO. But I mean, reproducing that is quite a task. And also, when you go closer to the limb, there are things are much more complicated because of the line of sight effect. So vector field measurements are somewhat restricted to smaller field of view, not full field of view. But for our kind of purpose, the line of sight magnetic field is good enough because, as I said, sunspots primarily field is vertical.
Every 20 minutes or so the vector.
Yeah.
But whether you need the information, extra information or not.
Yeah.
I had just one more question.
Yeah.
You had mentioned that image of which they reconstructed of the KSO, right? The false magnetic field image. Like, how did they do that?
Okay.
Yeah.
So there are many steps which was involved in that. One is the location identification by just identifying where the plages are, where the filaments are. So you know where the neutral, magnetic neutral lines are. So you have polarity information, you have this information. But then more important or harder task is the magnitude or the strength of the field, which is very, very hard. Because what you assume is the calcium, observation is somewhat, the intensity distribution will be somewhat linked with the magnetic field strength. So you do a calibration for a period where you have magnetic field information and calcium intensity information also. But unfortunately, it is not strictly linear. That's a problem. That if it is a linear relation, then you can do things much easily. But then people have to do it for small kind of field strength. You find some relation. For high field strength, you find some other relation. So it's a bits and pieces kind of a relation which has been constructed. So it's a reconstruction of the magnetic field strength to the calcium intensity variation, which is still far from, perfect, I would say.
So, here.
Piche.
Yeah. So you mentioned about recent theories explaining local dynamo versus global dynamo. So what would exactly classify as a local dynamo? I mean, are there like local toroidal fields around active regions, or what would
it has to be all over the sun? That's the thing. You see, it's just not active region alone. Because as I said, even in the absence of active region, you have all the flux concentration throughout the sun. So it is now has to be subsurface, but of course, magnetic field, you start with a very uniform field everywhere, and then you run the magnetic convection simulation. Then you will see that the small fluxes are actually going into the edges of the supergranules. We didn't talk about, probably you heard about network and, and so on. So these flux concentrations are getting as a natural, product of being segregated at the boundaries, and so those are the foot points of these flux tubes. So now, what is pumping these fluxes all the time has to have some dynamo. So
so they're like evenly distributed.
They have to be evenly distributed. It cannot be. So somehow there has to be a linkages with the global one and the local one, but still it is all speculation now. So only the probably full imagery simulations will be able to have this. So either they are able to reproduce, the big guys and the small guys. They are not able to do both self-consistently together because of the resolution limits and so on in the simulation.
So do they have like analogy to small and large eddies?
Yes. Yes. It's all related with convection,
Yeah.
So, you showed the 3D butterfly diagram, right? Can you explain it once, because the axis were
So basically it's a latitude, longitude, and the sizes was shown in the third axis.
Okay.
The big fellows versus the small fellows. The big fellows are there only in the low latitude, and the small fellows are there in the high latitude. So the size distribution also, because as I was indicating, that we are now trying to see that whether the big sunspots have some other origin, whether the small fellows are, getting marched together and the big sunspots are formed and so on.
Okay.
So statistically, we are trying to track the sunspots, which has not been done yet. This is just a first work has been done by one of our students. The paper is under review. These sunspots, they live for a certain number of days. Some live for a few days, some live for a few weeks. So we need to track these sunspots, see their growth and decay.
Okay.
And even their growth and decay may indicate their change in the tilt, how they are, because that tilt has something to do with how they're deeply anchored and so on.
Okay.
There's a lot of work to be done yet.
I had one more question. You showed the period of H-alpha observation from various observatories. In that, the KSO graph ends at somewhere in 2015 or something.
Yeah.
Oh,
So,
I-
yeah, unfortunately, the spectroheliogram observations we have stopped. So we became rich and we started making a new telescope. So that data has not been clubbed with this one yet.
Okay.
So as I said, uniform data from the spectroheliograph setup is for that period.
Okay.
After that, a new telescope has been procured and that data is there. But I have been using, H-alpha data from other sources.
Okay.
So that this, telescope is too small because you have much bigger, better quality data elsewhere.
Okay.
So we have up to date H-alpha data also merged.
Okay. Thank you.
Yeah.
Multi-application solar telescope, how do we measure the magnetic field strength?
Yeah. So that, as I said, it is based on spectropolarimetry. So they have spectropolarimetric observations. There they could measure all the 4 Stokes vector. And from the 4 Stokes vector, you can not only get the intensity, but you can get the magnetic field orientation and all that as well.
Yeah.
So that's a more modern way of doing magnetic field measurements from the spectropolarimetric. But then you should have a very good polarimeter because the percentage of polarization, what you measure from the solar, these spectral lines are very small. And then the other bigger problem is your instrument itself can introduce some polarimetry. So to measure a instrumental polarization is even more challenging and becomes, whatever results you produce becomes more unreliable because of that.
Is this instrument just fitted on this Aditya-L1?
No. Because of the fact also is that this is a Fabry-Perot instrument, which is risky to fly. So in Aditya, we have a standard grating. We have a polarizer as well, a rotating polarizer, not the this particular crystal which is there in the ground, because it has failed in the past in space. So that's why people do not want to take chances.
Can perhaps break for tea and continue the discussion over the tea, because the tea time is over and they're going away. So
Okay,
we can
okay.
continue the discussion.
Yeah.
over
So
tea.
what we'll do is, yes, it's 11:30.
We can still continue the questions after, because
Ha, ha.
speaker afterwards.
Right.
So we can
I'm continuing. So
Okay.
yeah.
All right.
Yeah.